Fact 1. You would be turned into human spaghetti if you fell into a black hole through a process called spaghettification. The gravitational force at your feet becomes significantly stronger than the force at your head because you are closer to the black hole's center. This difference in gravitational pull stretches your body vertically while simultaneously compressing it horizontally. Your feet accelerate faster toward the singularity than your head, creating a stretching effect that elongates your body like a piece of spaghetti. The tidal forces become so extreme that your molecular bonds break apart, first separating your limbs, then your organs, and finally your individual atoms. This horrifying process happens gradually as you approach the event horizon, with the stretching becoming more severe the closer you get to the center. Even your bones would snap under the immense differential forces before your body completely disintegrates into a stream of subatomic particles. Fact 2. Black holes can spin at nearly the speed of light, creating a phenomenon called frame, dragging that literally twists space and time around them. The fastest spinning black hole ever discovered rotates at 998 million meters per second at its equator, which is 99.7% the speed of light. This incredible rotation rate means the black hole completes over 1,000 rotations per second, faster than any object in the known universe. The spinning motion drags space-time itself along like honey being stirred with a spoon, creating a region called the ergosphere where nothing can remain stationary relative to distant observers. Even light gets caught in this cosmic whirlpool and is forced to rotate with the black hole. The frame dragging effect extends far beyond the event horizon, influencing the motion of stars and gas clouds thousands of light years away from the black hole itself. Fact 3. The largest black hole weighs as much as 100 billion suns compressed into a space that could fit our entire solar system 50 times over. Phoenix A star has an event horizon diameter of 590 billion kilometers, which means light would take over a week to travel from one side to the other. This supermassive black hole contains mass equivalent to 100 billion solar masses compressed into a region that dwarfs our solar system. The event horizon extends far beyond the orbit of Pluto, encompassing a volume so vast that Earth's entire orbit around the Sun would appear as a tiny speck within it. If you could somehow place this black hole at the center of our solar system, its event horizon would extend past the Kuiper Belt, swallowing all the planets, asteroids, and comets without even approaching its maximum size. The gravitational influence of such a massive object would be felt across hundreds of light years, affecting the motion of entire star systems. Fact 4. Black holes can shoot jets of plasma across entire galaxies at 99% the speed of light, creating the most powerful particle accelerators in the universe. These relativistic jets extend for millions of light years, carrying energy equivalent to billions of stars and traveling distances that span multiple galaxies. The jets form when magnetic fields around the black hole's accretion disk become twisted and compressed, creating a cosmic particle cannon that fires superheated plasma into space. Material in these jets reaches temperatures of billions of degrees, hot enough to strip electrons from atoms and create a stream of pure energy. The jets can punch through entire galaxy clusters, creating cavities in the intergalactic medium and influencing star formation across vast regions of space. Some jets are so powerful they can be detected from billions of light years away, making them among the brightest objects in the observable universe. Fact 5. A black hole the size of a coin would have more mass than Earth and would instantly destroy our planet through gravitational collapse. This hypothetical black hole would contain Earth's entire mass of 6 trillion kilograms compressed into a sphere smaller than a quarter. The gravitational field would be so intense that it would tear apart every atom on Earth's surface, pulling all matter toward the tiny black hole at incredible speeds. The process would take only minutes as Earth's crust, mantle, and core get stretched into thin streams of matter spiraling into the microscopic event horizon. The gravitational waves produced during this catastrophic event would ripple through spacetime, potentially detectable by gravitational wave observatories across the galaxy. Even the Moon would be pulled from its orbit and consumed within hours, leaving nothing but a coin-sized black hole where our entire planet once existed. Fact 6. Black holes can exist in binary pairs that spiral toward each other for millions of years, before colliding in the most violent events since the Big Bang. These cosmic dancers release more energy in gravitational waves during their final seconds than all the stars in the observable universe emit as light. The two black holes orbit each other at increasing speeds, losing energy through gravitational wave radiation until they reach orbital velocities of 30,000 kilometers per second. During the final merger, the black holes distort each other's event horizons, creating bizarre egg-shaped regions of no escape before combining into a single, larger black hole. The collision converts up to 5% of the total mass into pure gravitational wave energy, sending ripples through space-time that stretch and compress space itself. These waves travel at light speed across the universe, and when they reach Earth billions of years later, they cause detectors to move by distances smaller than 1/10,000th the width of a proton. Fact 7. Primordial black holes formed in the first fraction of a second after the Big Bang could be smaller than atoms yet contain the mass of mountains. These ancient relics formed from extremely dense regions of the early universe that collapsed under their own gravity before the first stars even existed. Unlike stellar black holes that require massive stars to create them, primordial black holes could form with any mass, from microscopic quantum-scale objects to supermassive giants. The smallest primordial black holes would have masses comparable to asteroids, but event horizons smaller than atomic nuclei, making them impossible to detect directly. These tiny black holes would evaporate almost instantly through Hawking radiation, exploding with the energy of millions of nuclear weapons. Some scientists theorize that primordial black holes could explain dark matter, the mysterious substance that makes up 85% of all matter in the universe, but has never been directly observed. Fact 8. The photon sphere around a black hole creates a region where light can orbit forever, trapped in an eternal circular path around the event horizon. This invisible boundary exists at exactly 1.5 times the radius of the event horizon, where the gravitational field is precisely strong enough to bend light into a perfect circle. Photons entering this region at the correct angle become permanently trapped, neither falling into the black hole nor escaping to infinity. Over millions of years, countless photons from stars, galaxies, and other light sources accumulate in this spherical shell, creating an invisible prison of light surrounding the black hole. If you could somehow see these trapped photons, the photon sphere would appear as a brilliant glowing shell, brighter than any star. Any slight disturbance would cause these photons to either spiral inward, past the event horizon, or escape outward, making the photon sphere an unstable equilibrium point in the curved spacetime around the black hole. Fact 9. Falling into a supermassive black hole would allow you to survive crossing the event horizon and potentially see the entire interior structure before reaching the singularity. Unlike smaller stellar black holes that would spaghettify you before you cross the event horizon, supermassive black holes have gentler tidal forces due to their enormous size. The event horizon of a billion solar mass black hole extends so far from the center that the gravitational gradient is relatively mild, allowing you to cross this boundary intact. Inside the event horizon, space and time become so warped that all directions lead toward the singularity, making escape impossible even in principle. You would experience the bizarre phenomenon where the normal concepts of space and time break down completely. The journey from the event horizon to the singularity could take hours or days from your perspective, during which you might observe the strange geometry of the black hole's interior before the inevitable. Encounter with infinite density destroys you. Fact 10. Black holes can act as cosmic lenses that magnify and distort the light from objects behind them, creating multiple images of the same galaxy or star. This gravitational lensing effect occurs because the black hole's immense gravity bends spacetime so severely that light rays follow curved paths around it. Astronomers have observed cases where a single galaxy appears as multiple arc-shaped images arranged in a ring around a black hole, with each image showing the galaxy at a different time due to the varying path lengths of light. The most extreme cases create Einstein rings, perfect circles of light formed when the black hole, background object, and observer are perfectly aligned. Some black holes can magnify background objects by factors of thousands, allowing astronomers to study galaxies and stars that would otherwise be too faint to detect. The distorted images can also reveal details about the black hole's mass and spin by analyzing how severely the light gets bent during its journey around the gravitational field. Fact 11. Black holes can steal matter from companion stars in binary systems, creating accretion disks that glow brighter than entire galaxies. When a black hole orbits close to a normal star, its gravitational field strips material from the star's outer layers, forming a spiraling disk of superheated gas around the black hole. This stolen matter accelerates to incredible speeds as it falls toward the event horizon, reaching temperatures of 10 million degrees Celsius and emitting intense X-ray radiation. The friction between particles in the accretion disk converts gravitational potential energy into heat and light with an efficiency of up to 40%, making black holes the most efficient energy converters in the universe. Nuclear fusion in stars only converts 0.7% of mass into energy, making black hole accretion disks nearly 60 times more efficient. The X-ray emissions from these feeding black holes can be detected across billions of light years, making them some of the brightest objects in the cosmos, despite being gravitational prisons from which nothing can escape. Fact 12. Intermediate mass black holes represent a mysterious missing link between stellar and supermassive black holes, with masses between 100 and 100,000 times our Sun. These elusive objects are extremely difficult to detect because they are too small to power bright quasars like supermassive black holes, but too large to form from single stellar collapse like stellar mass black holes. Scientists have found only a handful of confirmed intermediate mass black holes, leaving a puzzling gap in the black hole mass spectrum. Some may form when multiple stellar mass black holes merge together in dense star clusters, while others might be the remnants of the first generation of supermassive stars that existed in the early universe. These intermediate black holes could serve as seeds for the supermassive black holes found at galaxy centers, growing through accretion and mergers over billions of years. Their rarity suggests that the formation mechanisms for black holes in this mass range are either extremely uncommon or require very specific conditions that rarely occur in nature. Fact 13. The no-hair theorem states that black holes can only be described by three properties: mass, electric charge, and angular momentum, making them the simplest objects in the universe despite their terrifying nature. This theorem means that all other information about the matter that formed the black hole gets erased, including the chemical composition, temperature, density variations, and magnetic fields of the original material. Two black holes with identical mass, charge, and spin are completely indistinguishable, even if one formed from hydrogen gas and another from iron-rich stellar material. This simplicity creates the black hole information paradox, where quantum mechanics suggests that information cannot be destroyed, but general relativity indicates that anything falling into a black hole loses all distinguishing characteristics. The theorem implies that black holes have no surface features, no internal structure visible from outside, and no memory of their formation process. This makes them fundamentally different from every other object in the universe, which retain complex internal structures and histories of their formation and evolution. Fact 14. Sagittarius. A star, the supermassive black hole at the center of our galaxy, is relatively small and quiet compared to other galactic centers, containing only 4 million solar masses. This black hole sits 26,000 light-years from Earth and appears as a radio source no larger than the orbit of Mercury, despite its enormous mass. Unlike active galactic nuclei that power brilliant quasars, Sagittarius A star is currently in a dormant state, consuming very little material and producing minimal radiation. Astronomers can observe individual stars orbiting this black hole, with periods ranging from 16 years to several centuries, providing direct evidence of its gravitational influence. Some of these stars approach within 120 astronomical units of the event horizon, reaching speeds of up to 7,000 kilometers per second at their closest approach. The relatively calm nature of our galaxy's central black hole has allowed complex life to evolve on Earth, as active galactic nuclei can sterilize entire galaxies with their intense radiation and particle jets. Fact 15. Wormholes could theoretically connect black holes to white holes, creating tunnels through space-time that link different regions of the universe or even different universes entirely. These hypothetical structures, also called Einstein-Rosen bridges, would form when the extreme curvature of spacetime around a rotating black hole creates a passage to another location. The interior of a rotating black hole contains a ring-shaped singularity rather than a point, potentially allowing matter to pass through the center without being destroyed. However, these wormholes would be extremely unstable and would collapse faster than light could travel through them, making them useless for transportation. Even if they could remain open, the tidal forces and radiation inside would destroy any object attempting to traverse the tunnel. Some theoretical physicists propose that exotic matter with negative energy density could stabilize wormholes, but such matter has never been observed and may not exist in nature. The connection between black holes and white holes remains purely theoretical, as white holes have never been observed and may be impossible in our universe. Fact 16. Black holes can form from the direct collapse of massive gas clouds in the early universe without ever becoming stars, creating supermassive black holes that existed when the cosmos was less than 1 billion years old. These direct collapse black holes formed when pristine hydrogen and helium gas clouds with masses exceeding 100,000 suns collapsed under their own gravity in a single catastrophic event. Unlike stellar black holes that form from the death of massive stars, These primordial giants bypassed the stellar phase entirely, creating black holes with initial masses comparable to intermediate mass black holes. The process required very specific conditions in the early universe, including the absence of heavy elements that would have allowed the gas to cool and fragment into individual stars. These seed black holes then grew rapidly by accreting surrounding gas and merging with other black holes, eventually becoming the supermassive monsters we observe at the centers of ancient galaxies. The discovery of quasars, powered by billion solar mass black holes, less than 700 million years after the Big Bang, suggests that this direct collapse mechanism was crucial for creating the first generation of supermassive black holes. Fact 17. Micro black holes could theoretically be created in particle accelerators on Earth, but they would evaporate instantly in a burst of Hawking radiation equivalent to nuclear explosions. These laboratory-created black holes would have masses comparable to subatomic particles and event horizons smaller than the Planck length, the smallest meaningful distance in physics. A micro black hole with the mass of a proton would have a lifetime of only 10 to the minus 43 seconds before completely evaporating through the quantum effects. The energy released during this evaporation would be enormous relative to the black hole's tiny mass, following Einstein's mass-energy equivalence principle. Some theoretical models suggest that high-energy cosmic ray collisions in Earth's atmosphere might naturally create micro black holes that evaporate harmlessly before reaching the ground. The Large Hadron Collider and other particle accelerators operate at energies far below what would be required to create even the smallest black holes, making their artificial creation currently impossible with existing technology. However, if extra dimensions exist, as some theories propose, the energy threshold for black hole creation could be much lower than currently calculated. Fact 18. The firewall paradox suggests that the event horizon of a black hole might be surrounded by a wall of high-energy particles that would incinerate anything attempting to cross the boundary. This theoretical problem arises from the conflict between general relativity, which predicts that crossing the event horizon should be uneventful, and quantum mechanics, which requires that information falling into black holes must somehow be preserved. According to the firewall hypothesis, the quantum entanglement between particles inside and outside the black hole creates a barrier of intense radiation at the event horizon. This firewall would have temperatures exceeding billions of degrees, instantly vaporizing any matter that approaches the black hole's boundary. The paradox challenges our fundamental understanding of both gravity and quantum mechanics, suggesting that one of these well-tested theories must be incomplete or incorrect. Some physicists propose that the firewall only exists for old black holes that have evaporated more than half their original mass through Hawking radiation, while younger black holes would have normal, passable event horizons. Fact 19. Stellar mass black holes can be ejected from galaxies at speeds exceeding 1,000 kilometers per second through gravitational slingshot effects during galaxy mergers. These rogue black holes become wandering nomads in intergalactic space, carrying no accretion, disk, or companion stars to reveal their presence. The ejection occurs when three or more black holes interact gravitationally during the chaotic merger of two galaxies, with one black hole gaining enough kinetic energy to escape the combined gravitational pull of both galaxies. These hypervelocity black holes travel through the cosmic void for billions of years, invisible and undetectable, unless they occasionally encounter and consume stray gas clouds or rogue planets. Computer simulations suggest that millions of these ejected black holes may be wandering through the space between galaxies, representing a significant population of dark, invisible objects, Some of these rogue black holes might eventually fall back into other galaxies, contributing to the growth of supermassive black holes at galactic centers. The existence of wandering black holes adds an element of cosmic Russian roulette, as solar systems could potentially encounter these invisible gravitational monsters during their journeys through space. Fact 20. Black holes can create closed time-like curves in their interior regions, theoretically allowing time travel to the past and creating paradoxes that challenge causality itself. Inside a rotating black hole, the extreme warping of spacetime can create paths through four-dimensional spacetime that loop back to earlier times. These closed time-like curves would allow an object to travel into its own past, potentially creating grandfather paradox situations where effects precede their causes. The mathematics of general relativity permits these time loops in the region between the outer and inner event horizons of a rotating black hole, though the physical reality of such phenomena remains highly speculative. Quantum effects and the instability of the inner horizon might prevent the formation of closed time-like curves, preserving causality through mechanisms not yet fully understood. Some physicists propose that the universe has a built-in chronology protection mechanism that prevents time travel paradoxes, possibly through quantum fluctuations that destroy closed time-like curves before they can form. The possibility of time travel within black holes remains one of the most mind-bending and controversial predictions of Einstein's theory of general relativity. Fact 21. Black holes can merge with neutron stars in catastrophic collisions that forge heavy elements like gold and platinum while producing gravitational waves and gamma-ray bursts. When a black hole tears apart a neutron star, it creates a colonova explosion that synthesizes elements heavier than iron through rapid neutron capture processes. The neutron star's ultra-dense matter gets stretched into long tidal tails as the black hole's gravity overwhelms the neutron star's structural integrity. Most of the neutron star material falls into the black hole, but a small fraction gets ejected at high speeds, carrying newly formed heavy elements into space. These collisions occur roughly once every 100,000 years in a typical galaxy, making them the primary source of gold, platinum, uranium, and other precious metals in the universe. The gravitational waves from these mergers have different signatures than black hole collisions, allowing scientists to distinguish between the two types of cosmic catastrophes. A single neutron star black hole merger can produce several Earth masses worth of gold, explaining why these elements are relatively rare compared to lighter elements formed in stellar cores. Fact 22. The holographic principle suggests that all information contained within a black hole is encoded on its two-dimensional event horizon surface, challenging our understanding of three-dimensional reality. This mind-bending concept proposes that the three-dimensional interior of a black hole is actually a holographic projection of information stored on the spherical boundary. The principle emerged from studying black hole thermodynamics, where the entropy of a black hole is proportional to the area of its event horizon, rather than its volume. This relationship implies that the maximum amount of information that can be stored in any region of space is determined by the area of its boundary, not the volume it contains. The holographic principle has profound implications for our understanding of reality, suggesting that our three-dimensional perception of the universe might be an illusion created by information encoded on a distant two-dimensional surface. Some physicists speculate that our entire observable universe could be a holographic projection from information stored on a cosmic horizon, making reality fundamentally two-dimensional despite our three-dimensional experience. Fact 23. Quantum tunneling near black holes could allow virtual particle pairs to separate permanently, with one particle escaping as Hawking radiation, while its partner falls past the event horizon with negative energy. This process occurs because the intense gravitational field near the event horizon can provide enough energy to make virtual particle pairs real, violating the usual requirement that they annihilate each other almost instantly. The escaping particle carries positive energy away from the black hole, while the infalling particle has negative energy that reduces the black hole's total mass. Over astronomical timescales, this quantum mechanical process causes black holes to slowly evaporate, with smaller black holes radiating faster than larger ones. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning that stellar mass black holes are colder than the cosmic microwave background and actually absorb more energy than they emit. Only after the universe cools significantly in the far future will stellar mass black holes begin to lose mass through Hawking radiation, eventually exploding in a final burst of energy when they reach microscopic sizes. Fact 24. Supermassive black holes can launch relativistic jets that extend for millions of light years and influence star formation across entire galaxy clusters. These cosmic blowtorches carry magnetic fields and high-energy particles at speeds approaching the speed of light, creating cavities in the intergalactic medium that can be larger than entire galaxies. The jets interact with surrounding gas clouds, either triggering star formation through compression or suppressing it by heating the gas beyond the temperature threshold for gravitational collapse. Some jets are so powerful they can completely evacuate gas from galaxy clusters, preventing new stars from forming and effectively sterilizing vast regions of space. The energy output of these jets can exceed the total luminosity of their host galaxies by factors of thousands, making them visible across cosmological distances. Radio telescopes can detect the synchrotron radiation from these jets billions of light years away, providing insights into the feeding and growth patterns of supermassive black holes throughout cosmic history. The jets also serve as cosmic particle accelerators, producing ultra-high energy cosmic rays that travel throughout the universe and occasionally strike Earth's atmosphere. Fact 25. The ergosphere around rotating black holes creates a region where space-time itself is dragged along at such extreme speeds that nothing can remain stationary relative to distant observers. This zone exists between the event horizon and a larger boundary called the static limit, where the rotation of the black hole literally drags space and time around with it. Objects in the ergosphere are forced to rotate in the same direction as the black hole, even if they try to move in the opposite direction. The Penrose process allows objects to extract energy from rotating black holes by entering the ergosphere, splitting into two parts, and having one part fall into the black hole, while the other escapes with more energy than the original object possessed. This energy extraction mechanism could theoretically power advanced civilizations by allowing them to harvest rotational energy from black holes without crossing the event horizon. The ergosphere becomes larger and more pronounced for rapidly spinning black holes, with the most extreme cases having ergospheres that extend several times the radius of the event horizon. The frame-dragging effect in the ergosphere is so strong that it can twist magnetic field lines and accelerate particles to relativistic speeds. Fact 26. Black holes can create gravitational redshift so extreme that light from objects near the event horizon becomes stretched to radio wavelengths by the time it reaches distant observers. As photons climb out of the black hole's gravitational well, they lose energy and their wavelengths increase dramatically, shifting visible light through infrared, microwave, and eventually radio frequencies. An astronaut shining a flashlight near the event horizon would appear to emit radio waves to observers far from the black hole, even though the light appears normal from the astronaut's perspective. This gravitational redshift becomes infinite at the event horizon itself, meaning that light emitted exactly at the boundary would lose all its energy and never reach external observers. The effect allows astronomers to measure the strength of gravitational fields around black holes by observing how much the light from nearby matter gets redshifted. Matter spiraling into black holes often emits characteristic spectral lines that get progressively more redshifted as the material approaches the event horizon, providing a direct probe of the extreme space-time curvature. The redshift also explains why the accretion disks around black holes appear to have sharp inner edges, as light from matter closer to the event horizon gets redshifted beyond the detection limits of telescopes. Fact 27. Primordial black holes with masses smaller than asteroids would have completely evaporated by now through Hawking radiation, potentially contributing to the gamma-ray background observed throughout the universe. These microscopic black holes formed in the first moments after the Big Bang from quantum fluctuations in the primordial density field. Black holes with initial masses less than 10 to the 15th grams would have lifetimes shorter than the current age of the universe, exploding in bursts of high-energy particles and gamma rays. The final explosion of a primordial black hole releases energy equivalent to millions of hydrogen bombs in a fraction of a second, creating a distinctive signature that astronomers are actively searching for. If primordial black holes were abundant in the early universe, their evaporation could explain some of the unexplained gamma ray emissions detected by space-based telescopes. The search for evaporating primordial black holes represents one of the few ways to directly observe Hawking radiation, as stellar mass black holes are far too cold to produce detectable radiation. The absence of observed primordial black hole explosions places constraints on the density fluctuations in the early universe and the physics of black hole formation. Fact 28. Black holes can exist in hierarchical systems where smaller black holes orbit larger ones, creating complex gravitational dynamics that can eject stars from galaxies at hypervelocity speeds. These multi-black hole systems form during galaxy mergers when the supermassive black holes from each galaxy eventually settle into bound orbits around their common center of mass. The gravitational interactions in these systems can accelerate nearby stars to speeds exceeding 1,000 kilometers per second, fast enough to escape the galaxy entirely. Hypervelocity stars have been observed streaming away from the galactic center, providing evidence for the chaotic dynamics of multiple black hole systems. Some of these ejected stars carry planetary systems with them into intergalactic space, creating isolated stellar systems that will wander the cosmic void for billions of years. The three-body interactions between two supermassive black holes and individual stars can also change stellar orbits dramatically, sending some stars plunging directly into one of the black holes while flinging others to the outer reaches of the galaxy. Computer simulations show that these gravitational billiard ball effects can reshape entire galactic cores over millions of years. Fact 29. The black hole information paradox suggests that information falling into black holes might be destroyed forever, violating one of the fundamental principles of quantum mechanics that information must be conserved. When matter falls past the event horizon, all information about its quantum state appears to be lost permanently, creating a conflict between general relativity and quantum theory. Hawking radiation appears to be completely thermal and random, carrying no information about the matter that originally fell into the black hole. This paradox has puzzled physicists for decades because quantum mechanics requires that information about physical systems must always be preserved, even if it becomes scrambled or difficult to decode. Some proposed solutions include the idea that information is encoded in subtle correlations within the Hawking radiation, or that black holes don't actually destroy information, but store it in ways we don't yet understand. The firewall paradox represents another attempt to resolve this conflict by suggesting that the event horizon itself might not be the smooth boundary predicted by general relativity. The resolution of the information paradox could require a complete revolution in our understanding of gravity, quantum mechanics, or the nature of space-time itself. Fact 30. Rotating black holes can theoretically be used as cosmic batteries through the Penrose process, allowing advanced civilizations to extract up to 29% of the black hole's rest mass energy. This energy extraction method involves dropping material into the ergosphere of a spinning black hole, where it splits into two parts, with one piece falling past the event horizon, carrying negative energy, while the other escapes with more energy than the original material possessed. The process works because the ergosphere allows objects to have negative energy relative to distant observers while still having positive energy locally. Repeated applications of the Penrose process could gradually slow down the black hole's rotation, converting rotational kinetic energy into usable power for a Type II civilization on the Kardashev scale. The total energy available through this method for a maximally spinning solar mass black hole would be equivalent to the Sun's entire energy output for 10 billion years. Advanced civilizations might construct massive particle accelerators around rotating black holes to efficiently extract energy through controlled Penrose processes. This mechanism represents one of the most efficient energy sources possible in the universe, limited only by the rotational energy stored in the black hole's spin. Fact 31. Black holes can create gravitational lensing effects so powerful that they can magnify background galaxies by factors of thousands, allowing astronomers to observe objects that would otherwise be invisible. When a black hole passes directly between Earth and a distant galaxy, its gravitational field acts like a cosmic magnifying glass, bending and focusing the light from the background object. This gravitational microlensing can temporarily increase the brightness of distant stars and galaxies by enormous amounts, sometimes making them visible for the first time. The lensing effect also creates multiple images of the same object, with light taking different paths around the black hole and arriving at Earth at different times. Some gravitational lenses produce perfect Einstein rings, where the background object appears as a complete circle of light surrounding the lensing black hole. The time delays between multiple images can reveal information about the mass and distance of the lensing black hole, even if the black hole itself is completely invisible. Astronomers use these gravitational telescopes to study the most distant galaxies in the universe, observing them as they appeared when the cosmos was less than 1 billion years old. Fact 32. Supermassive black holes can completely disrupt the orbits of binary star systems that venture too close, tearing apart stellar pairs that have orbited each other for billions of years. When a binary star system approaches within a few hundred times the black hole's event horizon radius, the differential gravitational forces become strong enough to overcome the star's mutual gravitational attraction. One star typically gets captured into a tight orbit around the black hole, while its companion gets ejected at high velocity, sometimes reaching speeds of several thousand kilometers per second. The captured star often gets stretched and heated by tidal forces, creating a bright flare of X-ray and optical emission as it begins to spiral toward the black hole. These tidal disruption events can outshine entire galaxies for months or years as the stellar material forms an accretion disk around the black hole. The ejected companion star becomes a hypervelocity star that escapes the galaxy entirely, carrying with it the memory of its disrupted partnership. Astronomers have observed dozens of these stellar breakups, providing insights into the population of binary stars in galactic centers and the feeding patterns of supermassive black holes. Fact 33. The innermost stable circular orbit around a black hole represents the last possible location where matter can orbit without inevitably spiraling inward to destruction. For a non-rotating black hole, this critical radius exists at exactly 3 times the event horizon radius, while rapidly spinning black holes can have stable orbits much closer to the event horizon. Matter orbiting at this boundary moves at approximately half the speed of light and experiences gravitational forces millions of times stronger than Earth's surface gravity. Any material that falls below this radius cannot maintain a stable orbit and will spiral into the black hole within a few orbital periods, typically lasting only milliseconds. The innermost stable circular orbit marks the inner edge of accretion disks, explaining why these structures appear to have sharp boundaries when observed with X-ray telescopes. Material at this radius experiences extreme tidal heating and emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. The location of the innermost stable circular orbit depends on the black hole's spin, allowing astronomers to measure how fast supermassive black holes are rotating by observing the inner edges of their accretion disks. Fact 34. Black holes can form through the direct collapse of dark matter, halos in the early universe, creating supermassive black holes without requiring any normal matter or stellar processes. These dark matter black holes would form when primordial dark matter clumps became so dense that they collapsed under their own gravity, bypassing the usual stellar evolution pathway entirely. The process could create black holes with masses ranging from thousands to millions of solar masses directly from dark matter, providing seeds for the supermassive black holes observed in early galaxies. Unlike normal matter, dark matter cannot cool through radiation, making it difficult for dark matter halos to collapse to the extreme densities required for black hole formation. However, interactions with normal matter or other dark matter particles could potentially trigger the collapse process under specific conditions in the early universe. These hypothetical dark matter black holes would be indistinguishable from ordinary black holes once formed, as the no-hair theorem erases all information about their original composition. The existence of dark matter black holes remains speculative, but they could help explain how supermassive black holes grew so large so quickly in the early universe. Fact 35. Quantum effects near black holes can create particle-antiparticle pairs where the antiparticle falls into the black hole while the particle escapes, effectively allowing the black hole to evaporate through a process that violates classical physics. This Hawking radiation emerges from quantum vacuum fluctuations that occur everywhere in space, but become amplified by the extreme gravitational fields near event horizons. The escaping particles carry positive energy away from the black hole, while the infilling antiparticles have negative energy that reduces the black hole's total mass. The radiation has a perfect thermal spectrum with a temperature inversely proportional to the black hole's mass, making stellar mass black holes incredibly cold, while microscopic black holes would be extremely hot. For a solar mass black hole, the Hawking temperature is only 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation. The evaporation process accelerates as the black hole shrinks, with the final moments involving an explosive release of energy as the remaining mass converts entirely to radiation. This quantum mechanical process represents the only known mechanism by which black holes can lose mass and eventually disappear completely. Fact 36. Black holes can create closed time-like curves in their rotating interiors that theoretically allow objects to travel backward in time and encounter their own past, creating paradoxes that challenge the fundamental nature of causality. Inside the ergosphere of a maximally spinning black hole, the extreme frame dragging effects can twist space-time so severely that the normal flow of time becomes scrambled. An object following certain trajectories through this region could theoretically emerge from the black hole before it entered, violating the principle that effects must follow causes. These closed, time-like curves exist mathematically in the solutions to Einstein's field equations, but may be prevented by quantum effects or cosmic censorship mechanisms that protect causality. The grandfather paradox becomes a real physical possibility in these regions, where an object could theoretically prevent its own creation by interfering with past events. Most physicists believe that unknown physical processes must prevent the formation of closed, time-like curves, possibly through quantum fluctuations that destroy them before they can form. The existence of time travel within black holes remains one of the most controversial and mind-bending predictions of general relativity. Fact 37. Stellar mass black holes can be kicked out of their birth locations by asymmetric supernova explosions, receiving velocities of hundreds of kilometers per second that send them careening through space as cosmic nomads. When massive stars explode as supernovae, the explosion is often not perfectly symmetric, creating a net momentum that launches the resulting black hole in a specific direction. These natal kicks can give black holes velocities exceeding the escape speed of their host galaxies, ejecting them into intergalactic space where they wander alone for billions of years. Computer simulations suggest that up to half of all stellar mass black holes may have been ejected from their birth galaxies through this mechanism. These wandering black holes are nearly impossible to detect unless they encounter gas clouds or other matter that they can accrete, briefly revealing their presence through X-ray emissions. Some of these nomadic black holes may eventually fall into other galaxies, contributing to the population of stellar mass black holes in galactic halos. The existence of wandering black holes means that dangerous gravitational monsters could be lurking in the apparently empty space between galaxies, invisible until something crosses their path. Fact 38. The event horizon of a black hole acts like a one-way membrane that allows information to enter but never leave, creating a cosmic information trap that accumulates knowledge from across the universe. Every piece of matter that falls past the event horizon carries with it information about its quantum state, chemical composition, and history, all of which becomes permanently trapped inside the black hole. Over billions of years, supermassive black holes accumulate vast amounts of information from the stars, planets, and civilizations they consume, becoming cosmic libraries of everything that has ever fallen into them. The holographic principle suggests that this information might be encoded on the event horizon surface itself, with each bit of information corresponding to a Planck area patch on the boundary. If this is true, the event horizon of a supermassive black hole could contain more information than all the libraries, computers, and brains that have ever existed in the observable universe. The information paradox questions whether this trapped information is truly lost forever or whether it might somehow be recovered through Hawking radiation or other quantum processes. The resolution of this paradox could revolutionize our understanding of information, consciousness, and the fundamental nature of reality itself. Fact 39. Black holes can merge in hierarchical cascades where the products of smaller mergers combine to form even larger black holes, potentially creating supermassive giants through a cosmic assembly line process. In dense stellar environments like globular clusters or galactic nuclei, multiple stellar mass black holes can form a gravitationally bound system that gradually shrinks through gravitational wave emission. When two black holes in such a system merge, the resulting larger black hole can capture additional black holes, leading to a chain reaction of mergers that builds increasingly massive objects. These hierarchical mergers can produce intermediate mass black holes with masses between stellar and supermassive scales, filling the mysterious gap in the black hole mass spectrum. The gravitational waves from hierarchical mergers have distinctive signatures that differ from isolated binary mergers, allowing astronomers to identify these cosmic assembly processes. Computer simulations show that dense stellar clusters can produce black holes with masses exceeding 1,000 suns through repeated mergers over millions of years. This hierarchical growth mechanism may explain how some supermassive black holes reach billions of solar masses so quickly in the early universe. Fact 40. The singularity at the center of a rotating black hole takes the form of a ring rather than a point, creating a donut-shaped region of infinite density that might allow matter to pass through its center without being destroyed. This ring singularity, also called a Kerr singularity, forms because the centrifugal forces from the black hole's rotation prevent all the mass from collapsing to a single point. The ring has zero thickness but finite radius, with the size depending on the black hole's angular momentum and mass. Theoretical calculations suggest that objects falling into a rotating black hole might be able to pass through the center of the ring singularity and emerge into a different region of space-time. However, the extreme tidal forces and quantum effects near the ring singularity would likely destroy any real object long before it could complete such a journey. The ring singularity represents a breakdown in our understanding of physics, where general relativity predicts infinite curvature and density that cannot be physically meaningful. Most physicists believe that a complete theory of quantum gravity will resolve these infinities and reveal the true nature of black hole interiors. Fact 41. Black holes can create gravitational waves that ripple through spacetime at the speed of light, carrying energy away from the system and causing orbiting objects to spiral inward with mathematical precision. These waves stretch and compress space itself as they pass, alternately lengthening and shortening the distance between objects by amounts smaller than 1/10,000th the width of a proton. When two black holes orbit each other, they lose energy through gravitational wave radiation, causing their orbits to decay and their orbital speeds to increase dramatically. The final moments before merger involve the black holes circling each other hundreds of times per second, releasing more power in gravitational waves than all the stars in the observable universe emit as light. Advanced LIGO detectors can measure these tiny spacetime distortions by monitoring laser beams traveling between mirrors separated by 4 kilometers. The detection of gravitational waves has opened an entirely new window for observing the universe, allowing astronomers to study black hole mergers that occurred billions of years ago. Each gravitational wave detection provides precise measurements of black hole masses, spins, and distances, revealing the hidden population of black holes throughout cosmic history. Fact 42. Supermassive black holes can regulate star formation across entire galaxies through feedback mechanisms that either trigger or suppress the birth of new stars, depending on their activity level. When these giants actively accrete matter, they launch powerful jets and winds that heat the surrounding gas to temperatures exceeding 10 million degrees, preventing it from cooling and condensing into new stars. This negative feedback can completely shut down star formation in massive galaxies, explaining why the most massive galaxies in the universe contain predominantly old red stars. Conversely, the shock waves from black hole jets can compress gas clouds in other regions, triggering bursts of star formation that create new stellar nurseries. The mass of a galaxy's central supermassive black hole correlates strongly with the total mass of stars in the galaxy's central bulge, suggesting a fundamental connection between black hole growth and stellar formation. This relationship implies that supermassive black holes and their host galaxies evolve together through cosmic time, with each influencing the other's development. The feedback from supermassive black holes may be responsible for the observed upper limit on galaxy masses, preventing the formation of galaxies much larger than the Milky Way. Fact 43. Black holes can exist in stable orbits around each other for millions of years before finally merging, creating binary systems that slowly spiral inward while emitting gravitational waves continuously. These cosmic dances begin when two galaxies merge, and their central supermassive black holes eventually find each other through dynamical friction with surrounding stars and gas. The binary black holes can remain separated by distances of several light years for extended periods, with orbital periods ranging from thousands to millions of years. During this long in-spiral phase, the black holes gradually lose energy through gravitational wave emission, causing their orbits to shrink and their orbital speeds to increase. The process accelerates dramatically in the final stages, with the black holes completing their last few orbits in a matter of minutes before merging. Astronomers have discovered several candidate supermassive black hole binaries by observing periodic variations in quasar brightness caused by the orbital motion of the black holes. The merger of supermassive black hole binaries represents the most energetic events in the universe since the Big Bang, releasing energy equivalent to the annihilation of several solar masses. Fact 44. Primordial black holes could make up a significant fraction of dark matter, the mysterious substance that comprises 85% of all matter in the universe, but has never been directly detected. These ancient black holes would have formed from density fluctuations in the first fraction of a second after the Big Bang, before the first stars ever existed. Unlike particle dark matter candidates, primordial black holes would interact gravitationally with normal matter while remaining invisible to electromagnetic radiation. The mass spectrum of primordial black holes could range from microscopic quantum scale objects to supermassive giants, with different mass ranges contributing to various astronomical phenomena. Intermediate mass primordial black holes could explain the unexpected abundance of black hole mergers detected by gravitational wave observatories. The search for primordial black holes involves looking for their gravitational effects on light from distant stars, their contribution to the cosmic gamma ray background through Hawking radiation, and their role in structure formation in the early universe. If primordial black holes comprise a substantial fraction of dark matter, they would fundamentally change our understanding of cosmology and the nature of the universe's missing mass. Fact 45. Black holes can create accretion disk instabilities that produce quasi-periodic oscillations in their X-ray emissions, revealing information about the extreme physics near the event horizon. These oscillations occur when hotspots in the accretion disk orbit around the black hole at frequencies ranging from millihertz to kilohertz, creating lighthouse-like beams of X-ray radiation. The frequencies of these oscillations are directly related to the fundamental timescales of the black hole, including the orbital period at the innermost stable circular orbit and the precession of elliptical orbits in the curved spacetime. By analyzing the patterns of quasi-periodic oscillations, astronomers can measure black hole masses and spins with remarkable precision, even for systems too distant to resolve spatially. Some oscillations show harmonic relationships that provide insights into the three-dimensional structure of the accretion flow and the magnetic field configurations near the event horizon. The study of these oscillations has revealed that matter can orbit black holes in complex non-circular patterns that create intricate timing signatures in the observed radiation. These quasi-periodic oscillations serve as natural laboratories for testing general relativity in the strong field regime where Newton's laws completely break down. Fact 46. Black holes can create plasma instabilities in their accretion disks that generate magnetic field lines twisted into helical structures, launching matter outward at relativistic speeds through magnetohydrodynamic processes. These magnetic field configurations become wound up by the differential rotation of the accretion disk, where material closer to the black hole orbits faster than material farther out. The twisted magnetic fields store enormous amounts of energy that can be suddenly released through magnetic reconnection events, similar to solar flares but millions of times more powerful. When these magnetic field lines snap and reconnect, they accelerate charged particles to nearly the speed of light and launch them along the black hole's rotation axis as collimated jets. The process converts the rotational energy of the black hole itself into kinetic energy of the ejected plasma through the Blandford-Zanejek mechanism. These magnetized jets can maintain their coherence across distances of millions of light years, creating some of the largest structures in the universe. The magnetic field strength near stellar mass black holes can exceed 100 million times Earth's magnetic field, while supermassive black holes can generate fields billions of times stronger than any magnetic field achievable in terrestrial laboratories. Fact 47. Intermediate mass black holes can form through runaway stellar collisions in dense star clusters, where massive stars merge repeatedly until they exceed the theoretical upper limit for stellar mass and collapse directly into black holes. This process begins in young, compact star clusters, where stellar densities can exceed 1 million stars per cubic parsec, making close encounters and collisions inevitable. When two massive stars collide, they merge to form an even more massive object that becomes increasingly likely to collide with other stars due to its enhanced gravitational cross-section. The runaway collision process can build stars with masses exceeding 300 times the mass of the Sun, far beyond the normal upper limit of stellar mass set by radiation pressure. These supermassive stars have lifetimes of only a few million years before their cores collapse directly into intermediate mass black holes without undergoing a supernova explosion. Computer simulations show that this process can create black holes with masses between 100 and several thousand solar masses in dense stellar environments. The resulting intermediate mass black holes can then grow further through accretion and mergers, potentially serving as seeds for the supermassive black holes found at galaxy centers. Fact 48. Black holes can create gravitational redshift gradients so steep that different parts of an extended object experience dramatically different time dilation effects, causing the object to appear stretched and distorted to distant observers. An astronaut falling feet first toward a black hole would experience time passing normally from their own perspective, but observers watching from far away would see the astronauts' feet aging faster than their head due to the stronger gravitational field at lower altitudes. This differential time dilation becomes extreme near the event horizon, where a difference of just a few meters in altitude can correspond to vastly different rates of time passage. The effect would cause extended objects to appear increasingly elongated as they approach the black hole, with the lower portions seeming to move in slow motion relative to the upper portions. Light emitted from different parts of the falling object would be redshifted by different amounts, creating a rainbow effect where the feet appear redder than the head. This gravitational time gradient represents one of the most dramatic manifestations of Einstein's theory of relativity, where space and time become so warped that the normal concepts of simultaneity and uniform time flow completely break down. Fact 49. Supermassive black holes can launch relativistic jets that create radio lobes extending far beyond their host galaxies, inflating giant bubbles of hot plasma in the intergalactic medium that can persist for hundreds of millions of years. These radio lobes form when the jets from active galactic nuclei plow into the surrounding gas, creating shock waves that heat the material to temperatures exceeding 100 million degrees. The inflated lobes can span several million light years, making them larger than the galaxies that created them and visible to radio telescopes across cosmological distances. The energy required to inflate these structures is enormous, equivalent to the total energy output of the Sun over billions of years, demonstrating the incredible power of supermassive black holes. The radio lobes serve as fossil records of past black hole activity, revealing episodes of intense feeding that may have occurred millions of years ago. As the jets shut off when the black hole stops accreting matter actively, the radio lobes gradually fade and cool, but they can remain detectable for hundreds of millions of years. These structures play important roles in galaxy evolution by preventing gas from cooling and forming new stars, effectively regulating the growth of massive galaxies throughout cosmic history. Fact 50. Black holes can create space-time geometries so exotic that they violate the weak energy condition, allowing for the theoretical existence of traversable wormholes that could connect distant regions of the universe or even different universes entirely. These hypothetical structures require exotic matter with negative energy density to keep the wormhole throat open and prevent it from collapsing faster than light can travel through it. The exotic matter would need to violate all known energy conditions, possessing properties unlike any form of matter or energy observed in nature. Even if such exotic matter existed, the wormhole would be extremely unstable, collapsing at the slightest disturbance from infalling radiation or matter. Quantum effects near the wormhole throat would likely create a firewall of high-energy particles that would destroy any object attempting to traverse the passage. The construction of a stable, traversable wormhole would require a level of technological sophistication far beyond any conceivable civilization, involving the manipulation of space-time itself on cosmic scales. Despite these seemingly insurmountable challenges, the mathematical possibility of wormholes continues to fascinate physicists and represents one of the most speculative but intriguing predictions of Einstein's theory of general relativity. Fact 51. Black holes can create tidal disruption events when they tear apart entire stars that venture too close, stretching stellar material into long streams that wrap around the black hole multiple times before falling past the event horizon. When a star approaches within the tidal radius of a supermassive black hole, the differential gravitational forces overcome the star's self-gravity and rip it apart completely. The disrupted stellar material forms elongated streams that can extend for billions of kilometers, with some material falling directly into the black hole, while other portions get ejected at high velocities. The infalling debris creates a temporary accretion disk that can outshine the entire host galaxy for months or years as it spirals toward the event horizon. These stellar destruction events occur roughly once every 10,000 to 100,000 years per galaxy, making them relatively rare but spectacular phenomena. The light curves of tidal disruption events have characteristic signatures that allow astronomers to distinguish them from other transient phenomena, like supernova or gamma ray bursts. The study of these events provides insights into the population of dormant supermassive black holes that normally remain invisible due to their lack of surrounding matter. Fact 52. Black holes can exist as naked singularities without event horizons if they spin fast enough or have sufficient electric charge, creating regions where the laws of physics break down and become visible to the outside universe. The cosmic censorship hypothesis suggests that nature prevents naked singularities from forming, but mathematical solutions to Einstein's equations allow for their theoretical existence under extreme conditions. A naked singularity would have infinite density and curvature visible to distant observers, potentially allowing information to escape from regions where spacetime itself becomes undefined. These hypothetical objects would violate causality by allowing effects to propagate faster than light and could create closed time-like curves that permit time travel to the past. The formation of naked singularities would require precisely tuned initial conditions that may be impossible to achieve in realistic astrophysical scenarios. If naked singularities could exist, they would represent the ultimate breakdown of predictability in physics, where the future evolution of the universe becomes fundamentally unknowable. Most physicists believe that quantum effects or unknown physical processes must prevent naked singularities from forming, preserving the cosmic censorship principle that keeps the universe's most extreme physics hidden behind event horizons. Fact 53. Black holes can create gravitational memory effects where passing gravitational waves permanently alter the spacetime geometry around them, leaving lasting changes in the distances between objects even after the waves have passed. This phenomenon occurs because gravitational waves carry energy and momentum away from their sources, causing permanent shifts in the gravitational field that persist long after the wave has propagated to infinity. The memory effect manifests as a permanent displacement of test particles that were initially at rest, with the magnitude of the displacement depending on the energy and angular momentum carried away by the gravitational waves. Advanced gravitational wave detectors might be able to measure these memory effects, providing new information about the dynamics of black hole mergers and the nonlinear nature of general relativity. The gravitational memory effect represents a purely general relativistic phenomenon with no analog in Newtonian gravity or electromagnetic theory. Computer simulations of black hole mergers show that the memory effect can cause permanent changes in detector arm lengths that persist indefinitely after the gravitational wave signal has ended. This effect could provide a new way to study the properties of black holes and test Einstein's theory in the strong field regime, where gravitational effects become highly nonlinear. Fact 54. Black holes can form through the collapse of false vacuum bubbles in quantum field theory, creating regions where the fundamental constants of physics differ from their values in our observable universe. These vacuum decay black holes would form when metastable vacuum states undergo phase transitions that release enormous amounts of energy in localized regions. The energy density from vacuum decay could exceed the critical threshold for gravitational collapse, creating black holes with properties determined by the new vacuum state rather than ordinary matter. Inside these black holes, the masses of elementary particles, the strength of fundamental forces, and even the number of spatial dimensions could be completely different from our universe. The event horizons of vacuum decay black holes would prevent the altered physics from affecting the outside universe containing the exotic vacuum state within an isolated region of spacetime. These hypothetical black holes could provide natural laboratories for studying alternative physics and the landscape of possible vacuum states predicted by string theory. The formation of vacuum decay black holes remains highly speculative and would require extreme conditions that may not exist anywhere in the observable universe, but they represent fascinating theoretical possibilities at the intersection of quantum field theory and general relativity. Fact 55. Black holes can create Hawking radiation with non-thermal corrections that carry information about the black hole's interior, potentially resolving the information paradox through subtle correlations in the emitted particles. Recent theoretical work suggests that the Hawking radiation spectrum contains tiny deviations from perfect thermal emission that encode information about the matter that originally fell into the black hole. These information-carrying correlations would be extremely difficult to detect because they require analyzing the quantum entanglement between individual Hawking radiation particles emitted over the black hole's entire evaporation timescale. The information recovery process would be incredibly slow, with meaningful information only emerging after the black hole has evaporated more than half of its original mass through Hawking radiation. Advanced quantum computers might eventually be capable of extracting this encoded information by performing complex quantum error correction algorithms on collected Hawking radiation. The information would emerge in a highly scrambled form that would require exponentially complex decoding procedures to reconstruct the original quantum states of infallen matter. This resolution of the information paradox suggests that black holes are not perfect information destroyers, but rather extremely efficient quantum scramblers that preserve information in nearly unrecognizable forms. Fact 56. Black holes can create gravitational shear effects that stretch space itself in perpendicular directions simultaneously, causing circular objects to become elliptical as they pass through regions of curved spacetime near the event horizon. This tidal stretching occurs because different parts of an extended object experience slightly different gravitational accelerations, with the variation depending on the object's size and distance from the black hole. The shear becomes most pronounced in the strong field region close to the event horizon, where spacetime curvature changes rapidly over small distances. Unlike simple stretching in one direction, gravitational shear involves simultaneous compression and expansion in orthogonal directions, creating complex deformation patterns that have no analog in everyday experience. The effect becomes so extreme near stellar mass black holes that atomic bonds would be broken by the differential forces long before an object reaches the event horizon. Supermassive black holes produce gentler shear effects due to their larger size, potentially allowing extended objects to survive crossing the event horizon while still experiencing significant deformation. The mathematical description of gravitational shear involves the Weyl tensor, which characterizes the tidal effects of curved spacetime independently of local matter density. Fact 57. Black holes can undergo phase transitions similar to those in thermodynamics, where small black holes behave like gases with negative heat capacity, while large black holes act like liquids with positive heat capacity. This unusual thermodynamic behavior means that adding energy to a small black hole actually makes it cooler, while removing energy makes it hotter, violating our everyday understanding of temperature and energy relationships. The phase transition occurs at a critical mass where the black hole's heat capacity changes sign, corresponding to a black hole with a Hawking temperature equal to the surrounding radiation temperature. Below this critical mass, black holes are thermodynamically unstable and will either evaporate completely or grow by absorbing surrounding radiation, depending on their environment. Above the critical mass, black holes become thermodynamically stable and can exist in thermal equilibrium with their surroundings. The analogy with ordinary phase transitions suggests that black holes might undergo more complex thermodynamic phenomena, including critical points and phase coexistence regions. Understanding black hole thermodynamics has led to important insights about the relationship between gravity, quantum mechanics, and information theory, contributing to the development of the holographic principle and other fundamental concepts in theoretical physics. Fact 58. Black holes can create particle production through the Unruh effect, where accelerated observers near the event horizon detect thermal radiation even in regions that appear empty to distant observers. This quantum phenomenon occurs because the concept of vacuum depends on the observer's reference frame, with accelerated observers experiencing what appears to be a thermal bath of particles. Near a black hole's event horizon, the extreme gravitational acceleration causes infalling observers to detect Unruh radiation with temperatures that can exceed the Hawking temperature of the black hole itself. The Unruh effect demonstrates the deep connection between acceleration, temperature, and quantum field theory, showing that the distinction between empty space and thermal radiation depends fundamentally on the observer's motion. For stellar mass black holes, the Unruh temperature experienced by infalling observers can reach billions of degrees, far exceeding the tiny Hawking temperature of the black hole. This effect contributes to the complex quantum phenomena occurring near black holes and may play a role in the information paradox and firewall scenarios. The Unruh effect has been proposed as a mechanism for creating detectable signatures of black holes through the thermal radiation experienced by matter falling past the event horizon. Fact 59. Black holes can create space-time foam at the Planck scale, where quantum fluctuations of the gravitational field cause the smooth geometry of general relativity to break down into a chaotic, bubbling structure. At distances smaller than the Planck length of 10 to the minus 35 meters, the uncertainty principle allows virtual black holes to spontaneously appear and disappear, creating a quantum foam of space-time geometry. These quantum fluctuations become increasingly important near the singularities of black holes, where the curvature approaches the Planck scale and classical general relativity loses its validity. The space-time foam may prevent the formation of true singularities by providing a quantum mechanical cutoff that replaces infinite curvature with finite but extremely large values. Loop quantum gravity and other approaches to quantum gravity predict that space-time foam could resolve the singularity problem by creating discrete, granular structures at the smallest scales. The foam-like nature of quantum spacetime could also affect the propagation of light and matter near black holes, potentially creating observable signatures in gravitational waves or electromagnetic radiation. Understanding spacetime foam represents one of the key challenges in developing a complete theory of quantum gravity that unifies general relativity with quantum mechanics. Fact 60. Black holes can create gravitational rainbow effects where different frequencies of light follow slightly different paths through curved spacetime, causing white light to separate into its component colors near the event horizon. This chromatic gravitational lensing occurs because the refractive index of curved spacetime depends weakly on photon frequency, similar to how glass prisms separate white light into rainbows. The effect becomes most pronounced in the strong gravitational fields near black holes, where the extreme spacetime curvature creates measurable differences in the deflection angles for different wavelengths of light. High-energy gamma rays follow slightly different trajectories than low-energy radio waves when passing close to a black hole, creating spectral distortions that could be detectable with sensitive instruments. The gravitational rainbow effect provides a potential test of quantum gravity theories that predict frequency-dependent modifications to the propagation of light in curved spacetime. Some theories suggest that the effect could be enhanced near the event horizons of black holes, where quantum corrections to general relativity become most important. Observations of gravitational rainbow effects could reveal new physics beyond Einstein's theory and provide insights into the quantum nature of gravity and spacetime. Fact 61. Black holes can create gravitational Doppler effects so extreme that light from orbiting matter gets shifted across the entire electromagnetic spectrum, from gamma rays to radio waves, as it completes a single orbit around the event horizon. Matter in the innermost stable circular orbit around a stellar mass black hole moves at approximately 30% the speed of light, creating relativistic Doppler shifts that dramatically alter the observed frequency of emitted radiation. When the orbiting material moves toward Earth, its light gets blue shifted to higher frequencies, while material moving away gets redshifted to lower frequencies, creating a characteristic double-peaked spectral line profile. The Doppler shifts become so extreme near rapidly spinning black holes that X-ray emission can be shifted into the optical band when moving toward observers, while simultaneously being shifted into infrared wavelengths when moving away. These relativistic Doppler effects allow astronomers to measure the rotation rates of black holes by analyzing the broadened and skewed spectral lines from their accretion disks. The most extreme cases involve matter orbiting so close to the event horizon that the Doppler shifts span several orders of magnitude in frequency. Computer simulations show that the Doppler effect combines with gravitational redshift and relativistic beaming to create complex spectral signatures that encode detailed information about the black hole's mass, spin, and inclination angle. Fact 62. Black holes can create quantum entanglement networks that connect particles across vast distances through their shared history of interaction with the black hole's gravitational field. When particle pairs are created near the event horizon through quantum fluctuations, one particle may fall into the black hole, while its entangled partner escapes as Hawking radiation, maintaining quantum correlations across the event horizon boundary. These entanglement connections could theoretically link particles throughout the universe that have interacted with the same black hole at different times, creating a cosmic web of quantum correlations. The entanglement network grows more complex as the black hole evaporates, with each emitted Hawking radiation particle potentially entangled with multiple particles inside the black hole and with previously emitted radiation. Some theoretical physicists propose that these entanglement networks could provide a mechanism for information storage and retrieval that resolves the black hole information paradox. The quantum correlations might encode information about the black hole's entire history, including all the matter and energy that has ever fallen past the event horizon. Advanced quantum technologies might eventually be capable of exploiting these entanglement networks to extract information from evaporating black holes or to create quantum communication channels across cosmic distances. Fact 63. Black holes can create gravitational wave chirps with frequencies that sweep from infrasonic to ultrasonic ranges in fractions of a second during the final moments of binary mergers. The gravitational wave frequency equals twice the orbital frequency of the merging black holes, starting at a few hertz when the black holes are separated by hundreds of kilometers and rising to over 1000 hertz at the moment of merger. This rapid frequency evolution, called a chirp, encodes precise information about the masses and spins of the merging black holes through the rate at which the frequency increases. The chirp pattern is so distinctive that it allows gravitational wave detectors to distinguish black hole mergers from other sources of spacetime disturbances with remarkable accuracy. Different mass combinations produce characteristic chirp signatures, with more massive systems producing lower frequency chirps that evolve more slowly, while lighter systems create higher frequency chirps that sweep rapidly through the detector's sensitive band. The final moments of the merger produce the most intense gravitational waves, with peak strain amplitudes that can exceed 10 to the minus 21 at distances of hundreds of megaparsecs. Advanced data analysis techniques use matched filtering to extract these chirp signals from detector noise, enabling the detection of black hole mergers that occurred billions of years ago and billions of light years away. Fact 64. Black holes can create relativistic plasma instabilities in their magnetospheres that generate coherent radio emissions similar to pulsar signals, but with much higher luminosities and more complex temporal patterns. The rotating magnetic fields around spinning black holes can accelerate charged particles to ultra-relativistic energies, creating conditions similar to those found in pulsar magnetospheres but scaled up by factors of millions. These black hole pulsars would emit beams of coherent radio radiation that sweep across space as the black hole rotates, potentially creating lighthouse-like signals detectable across cosmological distances. The plasma physics near black holes involves magnetic field strengths exceeding 10 to the 8th Gauss and particle energies reaching 10 to the 20th electron volts, far beyond anything achievable in terrestrial laboratories. Magnetic reconnection events in black hole magnetospheres could produce radio bursts with peak luminosities exceeding 10 to the 40 watts, making them visible throughout the observable universe. The complex geometry of twisted magnetic field lines around rotating black holes could create multiple emission beams with different polarizations and temporal characteristics. Some fast radio bursts observed by radio telescopes might originate from these magnetospheric processes around distant black holes, though the connection remains speculative and requires further observational confirmation. Fact 65. Black holes can create gravitational lensing caustics where multiple light rays from the same source converge simultaneously, producing infinite magnification of background objects for brief moments when perfect alignment occurs. These caustic events happen when a black hole passes directly between Earth and a distant star, creating multiple images that merge and separate as the alignment changes. During caustic crossings, the apparent brightness of the background star can increase by factors of thousands or millions, making normally invisible objects detectable for hours or days. The caustic patterns depend on the detailed mass distribution of the lensing black hole and any surrounding matter, providing a way to probe the structure of dark, compact objects with exquisite precision. Gravitational microlensing surveys monitor millions of stars simultaneously, searching for the characteristic light curves produced by black hole caustic events. The duration and shape of caustic events encode information about the mass, distance, and proper motion of the lensing black hole, even when the black hole itself remains completely invisible. Some caustic events produce complex light curves with multiple peaks and valleys as different caustic structures pass across the source star, creating detailed maps of the gravitational field around the lensing object. Fact 66. Black holes can create gravitational wave echoes that bounce back and forth between the event horizon and the photon sphere, producing delayed secondary signals that arrive after the main gravitational wave burst from binary mergers. These echoes form when gravitational waves generated during the merger get trapped in the curved spacetime near the newly formed black hole, bouncing between the gravitational potential barriers created by the extreme curvature. The echo signals arrive with time delays proportional to the light travel time around the black hole's photon sphere, typically occurring milliseconds to seconds after the primary merger signal. Each successive echo becomes progressively weaker as energy is lost through gravitational wave emission and absorption at the event horizon. The detection of gravitational wave echoes would provide direct evidence for the existence of event horizons and could test alternative theories of gravity that predict different near horizon structures. Advanced gravitational wave detectors with improved sensitivity might be capable of detecting these faint echo signals, opening a new window into the quantum structure of black hole horizons. The absence or presence of gravitational wave echoes could distinguish between classical black holes and exotic alternatives like gravastars or fuzzballs that lack true event horizons. Fact 67. Black holes can create particle acceleration zones called magnetospheric gaps, where the electric field becomes so strong that it spontaneously creates electron-positron pairs from the quantum vacuum. These gaps form in regions where the magnetic field lines cannot support steady current flow, causing electric fields to build up until they exceed the critical field strength for pair production. The critical electric field strength for vacuum breakdown is approximately 10 to the 18th volts per meter, a value so extreme that it can only be achieved near the most rapidly spinning black holes. When electron-positron pairs are created in these gaps, they immediately get accelerated to ultra-relativistic energies by the intense electric fields, creating cascades of secondary particles through interactions with photons and magnetic fields. The particle cascades can produce gamma-ray emissions with luminosities exceeding 10 to the 38 watts, making them detectable across intergalactic distances. These magnetospheric processes might explain some of the highest energy gamma-ray sources observed in the universe, including blazars and gamma-ray bursts associated with black holes. The study of vacuum breakdown near black holes provides insights into quantum electrodynamics in extreme environments that cannot be replicated in any terrestrial laboratory. Fact 68. Black holes can create space-time vortices that drag inertial reference frames around the rotating mass, causing gyroscopes and other test objects to precess even when they are not in direct contact with any matter. This frame-dragging effect, also known as the Lense-Thirring effect, becomes extremely pronounced near rapidly spinning black holes where space-time itself is twisted into helical structures. The vorticity of space-time near a maximally spinning black hole can exceed 10 to the sixth radians per second, causing dramatic precession of orbital planes and spin axes of nearby objects. Satellites orbiting Earth experience tiny frame-dragging effects that have been measured by precision experiments like Gravity Probe B. But near black holes, the effect becomes millions of times stronger. The space-time vortex extends far beyond the event horizon, influencing the motion of stars and gas clouds at distances of thousands of gravitational radii from the black hole. Frame dragging can cause the orbital planes of binary systems to precess rapidly, creating observable signatures in the timing of pulsar signals and the polarization of emitted radiation. The extreme frame dragging near black holes represents one of the most dramatic confirmations of Einstein's prediction that mass and energy can twist the fabric of spacetime itself. Fact 69. Black holes can create quantum vacuum polarization effects, where virtual particle pairs in the quantum vacuum become real particles due to the intense gravitational tidal forces near the event horizon. The strong gravitational gradients can separate virtual electron-positron pairs before they have time to annihilate, converting vacuum fluctuations into real particles that carry energy away from the black hole. This process contributes to Hawking radiation, but also creates additional quantum effects that modify the structure of spacetime near the event horizon. The vacuum polarization becomes most significant for small black holes, where the curvature radius approaches the Compton wavelength of elementary particles. Quantum field theory predicts that vacuum polarization creates an effective stress-energy tensor that backreacts on the gravitational field, potentially modifying the geometry of spacetime near black holes. The polarized vacuum can also create birefringence effects, where the propagation of light depends on its polarization state, similar to the behavior of light in certain crystals. These quantum vacuum effects represent corrections to classical general relativity that become important when gravitational fields approach the Planck scale, providing potential tests of quantum gravity theories. Fact 70. Black holes can create gravitational wave memory bursts that cause permanent displacements in the positions of freely falling test masses, with the displacement persisting indefinitely after the gravitational wave has passed. This nonlinear memory effect occurs because gravitational waves themselves carry energy and momentum, causing a permanent change in the space-time metric that affects the relative positions of distant objects. The memory effect is proportional to the total energy radiated in gravitational waves during black hole mergers, with more energetic collisions producing larger permanent displacements. Advanced gravitational wave detectors might be able to measure these memory effects by monitoring the DC shift in their interferometer arm lengths that persists after the oscillatory gravitational wave signal has ended. The gravitational wave memory provides a direct measurement of the total energy and momentum carried away by gravitational waves, offering new tests of general relativity in the strong field regime. Computer simulations predict that the memory effect can cause permanent length changes of up to 10 to the minus 22 meters in kilometer scale detectors for nearby black hole mergers. The detection of gravitational wave memory would represent a major milestone in gravitational wave astronomy and could reveal new aspects of the nonlinear dynamics of curved spacetime. Fact 71. Black holes can create gravitational wave shadows where the eye's curvature of spacetime around massive objects blocks or deflects gravitational waves, creating regions of reduced signal strength similar to optical shadows cast by solid objects. When gravitational waves from distant black hole mergers pass near intervening massive objects like galaxy clusters or supermassive black holes, the waves get lensed and focused in complex patterns that create both bright spots and shadow regions. The gravitational wave shadows depend on the wavelength of the waves and the mass distribution of the lensing object, with longer wavelengths experiencing stronger deflection effects. Multiple gravitational wave detectors positioned around Earth could potentially map these shadow patterns, providing new information about the distribution of dark matter and the masses of intervening objects. The shadow effects become most pronounced when the gravitational wave source, lensing object, and detector are nearly aligned, creating caustic patterns similar to those observed in optical gravitational lensing. Computer simulations show that supermassive black holes can create gravitational wave shadows spanning angular scales of several arc minutes on the sky. The study of gravitational wave lensing and shadowing represents a new frontier in multi-messenger astronomy that combines gravitational wave detection with traditional astronomical observations. Fact 72. Black holes can create plasma wake-field acceleration, where charged particles surf on electromagnetic waves generated by the black hole's rotation, reaching energies that exceed those achievable in any terrestrial particle accelerator. The rotating magnetic fields around spinning black holes create traveling electromagnetic waves that can trap and accelerate charged particles over distances of thousands of kilometers. Particles riding these plasma wake fields can gain energies exceeding 10 to the 20 electron volts, approaching the theoretical maximum energy limits set by interactions with cosmic microwave background photons. The acceleration process is similar to Wakefield acceleration techniques used in advanced particle accelerators, but scaled up by factors of billions due to the extreme electromagnetic fields near black holes. These ultra-high energy particles contribute to the cosmic ray spectrum observed at Earth and may be responsible for the most energetic cosmic ray events ever detected. The plasma wake-field mechanism could explain how black holes produce particles with energies far exceeding what would be possible through simple gravitational acceleration alone. Observations of high-energy neutrinos and gamma rays from active galactic nuclei provide indirect evidence for these extreme particle acceleration processes occurring near supermassive black holes. Fact 73. Black holes can create temporal echoes where information about past events gets encoded in the geometry of spacetime and can be retrieved by analyzing the gravitational field structure around the black hole. These spacetime memories form because the extreme curvature near black holes creates lasting imprints of infalling matter and energy that persist long after the original events occurred. The gravitational field of a black hole contains subtle multipole moments that encode information about the mass distribution and angular momentum of all the matter that has ever fallen into it. Advanced gravitational wave detectors might be able to read these temporal echoes by measuring tiny perturbations in the black hole's gravitational field, caused by the historical accumulation of infalling matter. The echo information becomes increasingly scrambled and difficult to decode as more matter falls into the black hole. But quantum error correction techniques might eventually allow the reconstruction of past events. These temporal echoes represent a form of gravitational memory that could provide insights into the formation and evolution history of individual black holes. The study of spacetime echoes could also shed light on the information paradox by revealing how information about infalling matter gets encoded in the black hole's gravitational field structure. Fact 74. Black holes can create gravitational wave sirens that provide standard candles for measuring cosmic distances without requiring electromagnetic counterparts, revolutionizing our understanding of the expansion rate and geometry of the universe. The gravitational wave signals from binary black hole mergers contain precise information about the masses and distances of the merging objects encoded in the amplitude and frequency evolution of the waves. Unlike electromagnetic standard candles that can be dimmed by dust or affected by redshift uncertainties, gravitational waves propagate through the universe without significant absorption or scattering. The combination of gravitational wave distance measurements with independent redshift determinations from host galaxy observations provides a new method for measuring the Hubble constant and testing cosmological models. Gravitational wave sirens could resolve the current tension between different measurements of the universe's expansion rate by providing independent distance calibrations that are free from the systematic uncertainties affecting traditional methods. Future gravitational wave detector networks will be capable of detecting thousands of black hole mergers per year, creating a comprehensive map of cosmic distances and expansion history. The precision of gravitational wave distance measurements improves with the signal-to-noise ratio, potentially achieving percent-level accuracy for nearby events detected by next-generation instruments. Fact 75. Black holes can create quantum entanglement harvesting, where initially uncorrelated particles become entangled through their interaction with the curved spacetime and quantum fields near the event horizon. This phenomenon occurs because the vacuum state of quantum fields in curved spacetime differs from the vacuum in flat spacetime, creating correlations between particles in different regions that would not exist in the absence of the black hole. Two particles that pass near a black hole at different times can become quantum entangled through their shared interaction with the black hole's gravitational field and the modified vacuum state of quantum fields. The entanglement harvesting effect becomes stronger for particles that pass closer to the event horizon, where the space-time curvature and field correlations are most pronounced. This process could create networks of quantum entanglement that span large distances and persist long after the particles have moved far from the black hole. The harvested entanglement might be exploitable for quantum information processing applications, potentially allowing the creation of quantum communication networks that use black holes as entanglement sources. Understanding entanglement harvesting near black holes could provide new insights into the relationship between gravity, quantum mechanics, and information theory in extreme environments. Fact 76. Black holes can create gravitational wave glitches where sudden changes in the black hole's rotation rate produce abrupt frequency jumps in the emitted gravitational waves, similar to the timing glitches observed in pulsars, but with much more dramatic effects. These glitches could occur when the black hole's crust, if it exists as predicted by some quantum gravity theories, suddenly cracks and readjusts due to the immense rotational stresses. The frequency change in gravitational waves would be proportional to the change in the black hole's angular velocity, potentially creating detectable discontinuities in the wave pattern that persist for extended periods. Unlike pulsar glitches that involve neutron star crusts, black hole glitches would involve the fundamental structure of spacetime itself, making them far more exotic and theoretically challenging to understand. The detection of gravitational wave glitches would provide direct evidence for internal structure within black holes, challenging the no-hair theorem and suggesting that black holes may have more complex internal dynamics than currently understood. Computer simulations of rotating black holes in modified gravity theories predict that glitches could produce frequency changes of several percent in the emitted gravitational waves. The study of black hole glitches could reveal new physics beyond general relativity and provide insights into the quantum structure of spacetime near event horizons. Fact 77. Black holes can create dark photon production through axion photon conversion in the strong magnetic fields of their magnetospheres, potentially generating invisible dark matter particles that interact only weakly with ordinary matter. The intense magnetic fields near rotating black holes, which can exceed 10 to the 8th Gauss, provide ideal conditions for converting ordinary photons into hypothetical dark photons through quantum field mixing effects. These dark photons would carry energy away from the black hole system without producing detectable electromagnetic radiation, creating a hidden channel for energy loss that could affect the black hole's evolution. The conversion process depends on the strength of the magnetic field and the mass of the dark photon, with optimal conversion occurring when the photon wavelength matches the magnetic field coherence length. Dark photon production could explain some of the missing energy in black hole accretion processes and might contribute to the dark matter content of the universe. Laboratory experiments are beginning to search for axion photon conversion effects, but the extreme conditions near black holes could produce conversion rates millions of times higher than achievable on Earth. The detection of dark photon signatures from black holes would provide evidence for physics beyond the standard model and could reveal new connections between black holes and dark matter. Fact 78. Black holes can create space-time crystallization, where the extreme curvature near the singularity causes the smooth geometry of general relativity to break down into discrete, lattice-like structures at the Planck scale. This quantum crystallization occurs when the space-time curvature approaches the Planck scale, where quantum effects become comparable to gravitational effects, and the continuous description of spacetime loses its validity. The crystalline structure would consist of fundamental spacetime units with sizes on the order of the Planck length, creating a granular texture to space and time that could prevent the formation of true singularities. Loop quantum gravity and other approaches to quantum gravity predict that spacetime crystallization could resolve the singularity problem by providing a natural cutoff to the gravitational collapse process. The crystal structure might have preferred orientations and symmetries that affect the propagation of gravitational waves and the behavior of matter near black holes. Spacetime crystals could create discrete energy levels for gravitational systems, similar to how atomic crystals create electronic band structures in solid-state physics. The study of spacetime crystallization represents one of the most speculative frontiers in theoretical physics, requiring the development of new mathematical tools to describe the quantum geometry of curved spacetime. Fact 79. Black holes can create gravitational wave rainbows where different frequency components of the waves travel at slightly different speeds through curved spacetime, causing broadband gravitational wave pulses to disperse and spread out over time. This gravitational dispersion occurs because some quantum gravity theories predict that the effective speed of gravitational waves depends weakly on their frequency, similar to how light disperses when passing through glass prisms. The dispersion effects become most pronounced for gravitational waves that travel through regions of strong spacetime curvature or over cosmological distances where small frequency-dependent effects can accumulate. High-frequency gravitational waves might arrive slightly earlier or later than low-frequency components from the same source, creating measurable time delays that encode information about the quantum structure of spacetime. The detection of gravitational wave dispersion would provide direct evidence for quantum gravity effects and could distinguish between different theoretical approaches to unifying general relativity with quantum mechanics. Current gravitational wave detectors are beginning to achieve the sensitivity needed to search for these subtle dispersion effects in signals from distant black hole mergers. The absence of detectable dispersion in gravitational waves places strong constraints on theories that predict frequency-dependent modifications to Einstein's theory of general relativity. Fact 80. Black holes can create quantum tunneling cascades where particles near the event horizon tunnel through the gravitational potential barrier and escape to infinity, creating a runaway process that could cause rapid black hole evaporation under certain conditions. This quantum tunneling occurs because the gravitational potential near black holes creates barriers that particles can penetrate through quantum mechanical effects, even when they lack sufficient classical energy to escape. The tunneling probability depends exponentially on the height and width of the potential barrier, making it extremely sensitive to the detailed structure of spacetime near the event horizon. Some modified gravity theories predict that quantum corrections to general relativity could enhance the tunneling probability, potentially causing black holes to evaporate much faster than predicted by standard Hawking radiation. The tunneling cascade would begin when a few particles tunnel out of the black hole, slightly reducing its mass and making it easier for additional particles to escape through the lowered potential barrier. Computer simulations of quantum tunneling near black holes suggest that the cascade process could cause microscopic black holes to explode violently, rather than evaporate gradually through thermal Hawking radiation. The study of quantum tunneling cascades could provide new insights into the quantum mechanics of gravity and the ultimate fate of black holes in the far future. Fact 81. Black holes can create gravitational wavelensing networks where multiple black holes act as a cosmic interferometer, amplifying and focusing gravitational waves from distant sources through coordinated lensing effects. When gravitational waves pass through regions containing multiple black holes, each black hole acts as a gravitational lens that can focus or defocus the waves depending on the alignment geometry. The combined lensing effects from multiple black holes can create interference patterns that dramatically amplify the gravitational wave signal in certain directions while creating null zones in others. These natural gravitational wave interferometers could have baseline separations of thousands of light years, far exceeding any conceivable artificial detector and providing unprecedented angular resolution for gravitational wave astronomy. The lensing network effects become most pronounced when the wavelength of the gravitational waves is comparable to the separation between the lensing black holes. Computer simulations show that galaxy clusters containing multiple supermassive black holes could create complex lensing patterns that focus gravitational waves from background sources into highly magnified beams. The detection of gravitational wave lensing networks would open new possibilities for studying the distribution of black holes throughout the universe and could reveal gravitational wave sources that would otherwise be too weak to detect. Fact 82. Black holes can create temporal paradox zones in their interior regions where the normal ordering of cause and effect breaks down completely, allowing effects to precede their causes and creating logical contradictions that challenge our understanding of reality. These paradox zones form in the region between the inner and outer event horizons of rotating black holes, where the extreme curvature of spacetime creates closed, time-like curves that loop back to earlier times. An object following certain trajectories through these regions could theoretically interact with its own past, creating grandfather paradox situations where the object prevents its own existence. The mathematical solutions to Einstein's equations permit these paradoxical regions, but most physicists believe that unknown physical processes must prevent their formation to preserve causality. Quantum effects near the inner horizon might create firewalls or other barriers that destroy closed time-like curves before they can lead to paradoxes. Some theories propose that the universe has built-in chronology protections mechanisms that automatically prevent the formation of time travel paradoxes through quantum fluctuations or other processes. The existence of temporal paradox zones represents one of the most mind-bending predictions of general relativity and highlights the deep mysteries that remain in our understanding of time, causality, and the nature of spacetime itself. Fact 83. Black holes can create gravitational wave archaeology, where ancient merger events leave permanent signatures in the large-scale structure of spacetime that can be detected billions of years after the original collisions occurred. These archaeological signatures form because massive black hole mergers create gravitational wave bursts so powerful that they permanently alter the metric tensor of spacetime over vast regions. The spacetime distortions from primordial black hole mergers in the early universe could still be detectable today as subtle correlations in the cosmic microwave background radiation, or as preferred directions in the large-scale distribution of galaxies. Future gravitational wave detectors with extreme sensitivity might be able to detect the accumulated effects of billions of ancient black hole mergers by analyzing the statistical properties of space-time fluctuations. The gravitational wave archaeological record could provide insights into the formation and evolution of the first black holes in the universe, including primordial black holes that formed directly from density fluctuations in the early cosmos. These ancient gravitational wave signatures might reveal information about the physics of the early universe that is not accessible through any other observational method. The study of gravitational wave archaeology represents a new frontier in cosmology that could revolutionize our understanding of the universe's earliest epochs and the role of black holes in cosmic evolution. Fact 84. Black holes can create quantum vacuum engineering effects where the intense gravitational fields modify the properties of empty space itself, potentially allowing the extraction of energy from the quantum vacuum through carefully designed processes. The strong gravitational gradients near black holes can polarize the quantum vacuum, creating regions where virtual particle pairs are more likely to become real particles through the Schwinger effect. These vacuum modification effects could theoretically be harnessed by advanced civilizations to extract energy directly from empty space, providing a power source that does not require conventional matter or radiation. The vacuum engineering process would involve manipulating the gravitational field geometry around black holes to create optimal conditions for vacuum energy extraction. Some theoretical calculations suggest that the energy density available from vacuum engineering near black holes could exceed the energy density of nuclear reactions by many orders of magnitude. The practical implementation of vacuum engineering would require technology capable of precisely controlling gravitational fields and manipulating space-time geometry on macroscopic scales. The study of quantum vacuum effects near black holes could lead to revolutionary advances in energy production and propulsion technology, though such applications remain highly speculative and far beyond current technological capabilities. Fact 85. Black holes can create gravitational wave holography, where three-dimensional information about the black hole's interior structure gets encoded in two-dimensional gravitational wave patterns emitted from the system. This holographic encoding occurs because the gravitational waves carry information about the mass distribution, angular momentum, and other properties of the matter that created and feeds the black hole. The two-dimensional gravitational wave data contains sufficient information to reconstruct a three-dimensional model of the black hole's formation, history, and internal dynamics, similar to how optical holograms encode three-dimensional images in two-dimensional interference patterns. Advanced data analysis techniques using machine learning and quantum information theory might be able to decode this holographic information and reveal details about the black hole's interior that are normally hidden behind the event horizon. The holographic principle suggests that all the information contained within a black hole is encoded on its two-dimensional event horizon surface, and gravitational waves might provide a way to read this encoded information. The development of gravitational wave holography could revolutionize black hole astronomy by providing direct access to information about black hole interiors and the physics of extreme spacetime curvature. This technique might also reveal whether black holes truly have smooth event horizons or whether they possess more complex internal structures predicted by some quantum gravity theories. Fact 86. Black holes can create gravitational wave metamaterials where the curved spacetime around them acts like an artificial medium that can bend, focus, and manipulate gravitational waves in ways impossible with ordinary matter. The extreme curvature near black holes creates effective refractive indices for gravitational waves that depend on the wave frequency and propagation direction, similar to how engineered metamaterials manipulate electromagnetic waves. Multiple black holes arranged in specific configurations could create gravitational wave cloaking devices that render objects invisible to gravitational wave detection by routing the waves around them. The metamaterial properties emerge from the nonlinear nature of general relativity, where gravitational waves interact with the curved spacetime background created by massive objects. Advanced civilizations might theoretically engineer networks of black holes to create gravitational wave lenses, amplifiers, and other optical devices scaled up to cosmic proportions. The study of gravitational wave metamaterials could lead to new techniques for gravitational wave astronomy, including super-resolution imaging and the ability to focus weak signals from distant sources. These spacetime metamaterials represent a fusion of general relativity with concepts from condensed matter physics and could reveal new applications of curved spacetime geometry for information, processing, and communication. Fact 87. Black holes can create quantum error correction codes, where the information falling into them gets encoded in redundant quantum states that protect against decoherence and information loss through natural error correction mechanisms. The holographic principle suggests that information about the black hole's interior is stored redundantly across the entire event horizon surface, with each piece of information encoded in multiple overlapping regions. This redundant encoding acts like a quantum error correction code that can recover lost information even if parts of the encoding system are damaged or destroyed. The error correction process occurs naturally through the dynamics of quantum fields near the event horizon, where entanglement between different regions of the horizon surface creates the necessary redundancy. Hawking radiation might carry error-corrected information that allows the complete reconstruction of everything that has ever fallen into the black hole, resolving the information paradox through quantum error correction. The black hole error correction code would be far more sophisticated than any artificial quantum error correction scheme, potentially providing blueprints for building ultra-reliable quantum computers and communication systems. Understanding how black holes implement quantum error correction could revolutionize quantum information science and provide new insights into the fundamental relationship between information, entropy, and gravity. Fact 88. Black holes can create space-time wormhole networks that connect different regions of the universe through quantum entanglement, potentially allowing instantaneous communication and travel across cosmic distances. These entanglement-based wormholes, called Einstein-Rosen bridges, form when two black holes become maximally entangled through their shared quantum states and gravitational interactions. The wormhole connection exists in a higher dimensional space that bypasses the normal three-dimensional geometry of our universe, creating shortcuts through space-time that could dramatically reduce travel times between distant locations. The traversability of these quantum wormholes depends on exotic matter with negative energy density that keeps the wormhole throat open against gravitational collapse. Some theoretical physicists propose that the interior of black holes might be connected to the interiors of other black holes through these quantum wormhole networks, creating a hidden cosmic web of space-time connections. The wormhole network could provide a mechanism for information transfer that preserves quantum entanglement across arbitrary distances, potentially explaining some of the mysterious correlations observed in quantum mechanics. The study of quantum wormhole networks represents one of the most speculative areas of theoretical physics, combining general relativity, quantum mechanics, and string theory in ways that challenge our understanding of space, time, and causality. Fact 89. Black holes can create gravitational wavetime crystals where the space-time geometry around them exhibits periodic structure in time that repeats indefinitely without any external energy input. These temporal crystals form when the gravitational field of a rotating black hole creates standing wave patterns in space-time that oscillate with the black hole's rotation frequency. The time crystal structure breaks the normal symmetry of time translation, creating preferred moments in time when the gravitational field strength reaches maximum and minimum values. Unlike ordinary crystals that have periodic structure in space, gravitational wavetime crystals have periodic structure in time while maintaining spatial homogeneity. The time crystal behavior emerges from the nonlinear dynamics of general relativity, where the black hole's rotation creates self-sustaining oscillations in the space-time metric. These temporal structures could store and process information in ways that are impossible with conventional matter-based systems, potentially leading to new forms of computation that exploit the periodic nature of time itself. The detection of gravitational wave-time crystals would provide evidence for exotic phases of space-time that have no analogue in ordinary condensed matter physics and could reveal new applications of curved space-time geometry for information storage and processing. Fact 90. Black holes can create quantum space-time foam bubbles where microscopic regions of space-time undergo rapid expansion and contraction cycles that create virtual universes lasting for Planck time intervals. These foam bubbles form when quantum fluctuations in the gravitational field become amplified by the extreme curvature near black hole singularities, creating temporary pockets of inflating space-time. Each foam bubble contains its own set of physical laws and fundamental constants that may differ from those in our observable universe, creating a multiverse of microscopic pocket universes. The foam bubbles typically collapse back into the parent spacetime within one Planck time, but some might undergo eternal inflation and grow into full-sized universes disconnected from our own. The quantum foam structure near black holes could provide a mechanism for universe creation, with each black hole potentially spawning countless baby universes through quantum tunneling processes. The study of space-time foam bubbles requires a complete theory of quantum gravity that unifies general relativity with quantum mechanics at the Planck scale. These microscopic universes represent the ultimate frontier in theoretical physics, where the concepts of space, time, and reality itself become fluid and subject to quantum uncertainty principles that govern the fundamental structure of existence. Fact 91. Black holes can create gravitational wave superradiance, where rotating black holes amplify electromagnetic and gravitational waves that pass through their ergosphere, extracting rotational energy and potentially creating runaway instabilities that could destroy the black hole. This superradiant amplification occurs when waves with specific frequencies and angular momentum enter the ergosphere and get scattered with more energy than they originally possessed. The amplified waves carry away rotational energy from the black hole, gradually slowing down its spin and reducing the size of the ergosphere until the superradiant condition is no longer satisfied. Massive scalar fields around rotating black holes can create superradiant instabilities that grow exponentially, forming dense clouds of scalar particles that could eventually collapse into smaller black holes or explode in energetic bursts. The superradiant process could theoretically be used by advanced civilizations to extract energy from rotating black holes by sending carefully tuned electromagnetic waves into the ergosphere and collecting the amplified radiation. Computer simulations show that superradiant instabilities could completely halt the rotation of supermassive black holes over cosmological timescales, fundamentally altering their properties and observable signatures. The study of superradiant amplification provides insights into the stability of rotating black holes and could reveal new mechanisms for energy extraction from these cosmic powerhouses. Fact 92. Black holes can create quantum entanglement, firewalls paradoxes, where the requirement to preserve quantum information creates walls of high-energy radiation at the event horizon that would incinerate anything attempting to cross the boundary. This firewall forms because maintaining quantum entanglement between Hawking radiation particles and the black hole interior requires breaking the entanglement between infalling matter and outgoing radiation. The resolution of this entanglement conflict creates a barrier of particles with energies approaching the Planck scale, effectively turning the event horizon into an impenetrable wall of destruction. The firewall paradox represents a fundamental conflict between the equivalence principle of general relativity, which predicts smooth passage through event horizons, and the unitarity principle of quantum mechanics, which requires information conservation. Some proposed solutions involve modifications to the structure of spacetime near black holes or changes to our understanding of quantum entanglement across event horizons. The firewall could be a temporary phenomenon that only exists for old black holes that have radiated away more than half their original mass through Hawking radiation. The resolution of the firewall paradox could require a complete revolution in our understanding of gravity, quantum mechanics, or the fundamental nature of information and reality itself. Fact 93. Black holes can create gravitational wave dark sirens, where merging black holes produce gravitational waves without any electromagnetic counterparts, providing independent measurements of cosmic distances and expansion rates through statistical analysis of large populations. These dark sirens occur when binary black holes merge in regions devoid of gas and stars, producing no optical, X-ray, or gamma-ray emissions that could provide redshift measurements. The gravitational wave signal alone contains information about the luminosity distance to the merger, but determining the cosmological redshift requires statistical techniques that correlate the observed merger rate with theoretical predictions. Large samples of dark siren events can constrain cosmological parameters by comparing the observed distribution of merger distances with models of cosmic structure, formation, and black hole evolution. Future gravitational wave detector networks will detect thousands of dark siren events per year, creating a comprehensive catalogue of cosmic distance measurements that are independent of traditional electromagnetic methods. The dark siren technique could resolve current tensions in measurements of the Hubble constant by providing a completely independent calibration of the cosmic distance ladder. These invisible standard candles represent a new tool for precision cosmology that exploits the fundamental physics of gravitational wave propagation through curved spacetime. Fact 94. Black holes can create quantum vacuum birefringence, where the intense gravitational and electromagnetic fields near the event horizon cause empty space to behave like a birefringent crystal that affects the polarization of light passing through it. This vacuum birefringence occurs because virtual particle pairs in the quantum vacuum become aligned by the strong fields, creating an effective medium with different refractive indices for different polarization states of light. The effect becomes most pronounced near magnetized black holes, where both gravitational tidal forces and electromagnetic fields contribute to the vacuum polarization. Light waves with different polarizations travel at slightly different speeds through the polarized vacuum, causing initially unpolarized light to become polarized and creating rotation of the polarization plane for initially polarized light. The vacuum birefringence effect provides a direct probe of quantum electrodynamics in extreme environments that cannot be replicated in terrestrial laboratories. Observations of polarized light from matter near black holes could reveal signatures of vacuum birefringence, providing tests of quantum field theory predictions in strong gravitational and electromagnetic fields. The detection of vacuum birefringence would confirm fundamental predictions of quantum electrodynamics and could reveal new physics beyond the standard model in extreme field environments. Fact 95. Black holes can create spacetime phase transitions where the geometry of curved spacetime undergoes sudden changes similar to phase transitions in condensed matter systems, potentially creating topological defects and exotic spacetime structures. These phase transitions occur when the spacetime curvature reaches critical values where the mathematical description of geometry becomes unstable and transitions to a different topological configuration. The phase transition could involve changes in the number of spatial dimensions, the signature of the spacetime metric, or the connectivity of different regions of spacetime. Topological defects created during spacetime phase transitions could include cosmic strings, domain walls, and monopoles made of pure geometry rather than matter or energy. The phase transition process might resolve singularities by replacing infinite curvature with finite but discontinuous changes in spacetime geometry. Computer simulations of spacetime phase transitions require advanced numerical techniques that can handle the breakdown of conventional geometric descriptions near critical points. The study of spacetime phase transitions represents a frontier area where general relativity meets condensed matter physics, potentially revealing new states of spacetime that have no analog in ordinary matter systems. Fact 96. Black holes can create gravitational wave memory palimpsests where multiple merger events create overlapping permanent spacetime distortions that encode a historical record of cosmic collisions spanning billions of years. These memory palimpsests form because each gravitational wave burst leaves a permanent displacement in the spacetime metric that persists indefinitely, with subsequent events adding additional layers of distortion. The accumulated memory effects from countless black hole mergers throughout cosmic history create a complex pattern of spacetime distortions that encodes information about the merger rate evolution and black hole population statistics. Advanced gravitational wave detectors might be able to decode these memory palimpsests by analyzing the statistical properties of spacetime fluctuations and separating the contributions from different historical epochs. The memory palimpsest provides a fossil record of gravitational wave activity that extends back to the earliest epochs of cosmic structure formation when the first black holes began merging. The decoding of gravitational wave memory palimpsests could reveal information about primordial black holes, the formation of the first galaxies, and the evolution of cosmic structure that is not accessible through any other observational method. This spacetime archaeology represents a new frontier in cosmology that exploits the permanent nature of gravitational wave memory effects. Fact 97. Black holes can create quantum entanglement, harvesting cascades where particles become entangled through their sequential interactions with the black hole's gravitational field, creating networks of quantum correlations that span vast distances and time intervals. This cascading entanglement occurs when particles that pass near the black hole at different times become correlated through their shared interaction with the modified vacuum state of quantum fields in curved spacetime. The entanglement cascade can create quantum correlations between particles that have never directly interacted linking them through their common history of gravitational interaction with the black hole. The cascade effect becomes stronger for particles that pass closer to the event horizon, where the spacetime curvature and quantum field correlations are most pronounced. These entanglement networks could persist long after the particles have moved far from the black hole, creating a web of quantum correlations that connects matter throughout the universe. The harvested entanglement might be exploitable for quantum information processing applications, potentially allowing the creation of quantum communication networks that use black holes as entanglement distribution centers. Understanding entanglement, harvesting cascades could provide new insights into the relationship between gravity, quantum mechanics, and information theory in extreme environments. Fact 98. Black holes can create gravitational wave metamaterial cloaking, where carefully arranged masses around the black hole can render it invisible to gravitational wave detection by routing the waves around the system without distortion. This cloaking effect works by creating a coordinate transformation that maps the space around the black hole to a region of flat spacetime, effectively hiding the black hole's gravitational signature from distant observers. The metamaterial cloaking requires exotic matter with carefully tuned mass and energy densities that create the precise spacetime curvature needed to bend gravitational waves around the hidden region. The cloaked black hole would be completely invisible to gravitational wave detectors, appearing as empty space even when other black holes merge nearby, or matter falls into the hidden system. Natural gravitational wave cloaking could occur in dense stellar environments where the collective gravitational field of many objects creates the necessary spacetime geometry for wave routing. The study of gravitational wave cloaking combines concepts from general relativity with transformation, optics, and metamaterial physics, potentially leading to new applications in gravitational wave astronomy. Advanced civilizations might theoretically use gravitational wave cloaking to hide their activities from detection by other technological species using gravitational wave telescopes. Fact 99. Black holes can create quantum vacuum engineering laboratories where the extreme conditions near the event horizon allow the study and manipulation of fundamental physics processes that are impossible to investigate anywhere else in the universe. The intense gravitational fields, high temperatures, and strong electromagnetic fields near black holes create natural laboratories for testing quantum field theory, general relativity, and potential theories of quantum gravity under the most extreme conditions possible. These cosmic laboratories provide access to energy scales and field strengths that exceed anything achievable in terrestrial particle accelerators or laboratory experiments by many orders of magnitude. The vacuum near black holes undergoes polarization, pair production, and other quantum effects that reveal the fundamental structure of spacetime and matter at the smallest scales. Advanced civilizations might use black holes as natural particle accelerators and field generators for conducting experiments in fundamental physics that would be impossible with artificial equipment. The study of quantum vacuum engineering near black holes could lead to revolutionary advances in our understanding of the universe and potentially enable new technologies based on the manipulation of spacetime and quantum fields. These natural laboratories represent the ultimate frontier for experimental physics, where the most fundamental laws of nature can be tested under conditions that approach the limits of physical possibility. Fact 100. Black holes can create universe-spawning mechanisms where quantum tunneling processes near the singularity create baby universes that inflate into separate spacetime regions completely disconnected from our observable cosmos. This cosmic reproduction occurs when quantum fluctuations in the gravitational field become amplified by the extreme curvature near black hole singularities, creating regions of false vacuum that undergo rapid inflation. Each baby universe begins as a microscopic bubble of spacetime that tunnels through the quantum barrier, separating different vacuum states, then inflates exponentially to macroscopic size through a process similar to cosmic inflation. The baby universes inherit physical constants and laws of physics that may differ from those in the parent universe, creating a multiverse of pocket universes with diverse properties and evolutionary histories. The universe spawning process could explain the origin of our own cosmos as the product of a black hole in a parent universe with different physical laws and dimensional structure. Each black hole in our universe might be creating countless baby universes through this quantum reproduction mechanism, making black holes the ultimate creative forces in the multiverse. The study of universe spawning represents the intersection of black hole physics, quantum cosmology, and multiverse theory, potentially revealing the deepest connections between gravity, quantum mechanics, and the fundamental nature of existence itself.